for the lab, you need to purchase some materials. I shared it on Tuesday, I shared it on Wednesday, and I'm going to share it with you again so that you know where to find it. You essentially have the links that you can use to purchase them. So I'm going to share my screen at this time. I'm going to go to the course. Can you see my screen? Okay, so again, here in this lab session, we said if you click on the first module, which is welcome and course materials, and you go through that, you will find a page that details the supplies. Okay, that's one way to find it. I also created an announcement with that same information as well. And so I'll show you this. So again, here on this page, you can see we have the link for the kit at the top right here. It's an Amazon product. And so this is the kit that you need. Secondly, you need to have a multimeter. And so we have two links for multimeters at the bottom here. And this is so that you can do your experiments at home, so that you can follow with me, you can follow the instructions I give you, and you can not only have a theoretical understanding of the circuits, but you can build them yourself. You can learn how to use the meter yourself and so forth. If you go also, an easier way to find it, if you go in announcements, so I click on announcements on the left here, you see there is an announcement that says information for purchasing kit for class. So I need you to purchase this kit this week, so you can have it at least by next week, so you can start working on the experiments. Again here, this kit is mandatory, so it is very important that you get it as soon as possible. Again, the links are here so you can purchase it. And this is what it looks like. So inside of this kit, you have a microcontroller that we'll use to supply 5 volts. So we're using USB power for this entire lab. And so we have a microcontroller here. We also have a breadboard that we use to make connections for our circuit. And we have a number of resistors. And these are the components that we'll be using for our circuits, right? We have some jumpers here that we also use to make connections. We have some LEDs that, of course, we're going to use for indication. We also use them when we do our project with the microcontroller, which is the programming project. And then we have some buttons and some other sensors as well. On this side, there are two options of multimeters that I gave you. We have this is a multimeter from Amazon, and this one is from Harbor Freight. Both of them are sufficient for the experiments that we'll be doing. So this is what I wanted to share with you. It's very important that you go ahead and take care of this as soon as possible. Any questions about this kit and about these materials? Like I said, we need these materials so that we can complete the experiments that we have for this course. Are there any questions?
No, sir.
All right. Okay, so that is the easiest part of this course, is to get the kit. Let's go on to the first module for the course. So if you click on Introduction to Lab Safety. So being the first module, we have not done anything, and I'm thinking you don't have your kits yet. We want to talk about electricity and about safety. The first module in the class is about energy. It's about also efficiency as well, right? It talks about how energy is generated, how it's transported from one point to the next. It talks about why we use electrical energy versus other forms of energy, why we use it for transmission and so forth. And of course, it talks about efficiency. And efficiency deals with the conversion of electric energy into other forms of energy. For example, converting electrical energy into kinetic energy, where we have motion, converting electrical energy into light energy for lighting and for so many other purposes. Now, efficiency tells us how well we are able to convert that electrical energy into the desired energy. Say, and the example I like to use is with a light bulb. A light bulb, the efficiency of a light bulb tells us how well that light bulb is able to convert electric energy into light energy. So the goal is to have 100% efficiency, but for most processes, we do not have 100% efficiency. So if you have 100 joules of electric energy and you want to convert that into 100 joules of light energy, your light bulb will probably give you 80 joules of light energy, and the rest of the energy will be converted into heat or into another form. So the energy is not destroyed, but rather it's created into another. It's converted into another form that is not desirable. And so efficiency tells you how much of your energy is converted into the desired form. And of course, you want to have the efficiency as high as possible. So in the first module for the class, the exercises ask you about, efficiency of different products in your home and so forth. And it also takes you to the Department of Energy's some of the recommendations that they give concerning energy efficiency. Okay, so again here in this first lab, we're discussing lab safety. So let's look at the overview briefly. Of course, we want to introduce the course and introduce the participants.
Welcome to the School of Electrical and Electronic Engineering Practical Labs. Please consider the following health and safety information while working in the labs. Before you begin working, make sure your bench is clean and clear. Food and drink are not allowed in the labs. Before soldering, turn on the extractor fan, which will remove any contaminants from the air. These are located under the bench. Don't inhale solder fumes, since although they are not toxic, they will irritate your throat and lungs. If the extractor head is too far away, it won't clear the fumes. Put the head close to the working area. Remember that apart from the handle, the whole soldering iron will get hot. Use the wet sponge on the iron holder to clean the tip. Never flick the iron to remove the solder, because you can't predict which direction the solder will fly in. And contact with the skin can cause serious burns. Safety glasses are provided. Always replace the soldering iron back into the holder, since putting it on the bench is hazardous in many ways. Always be conscious of the electrical hazard posed by the cables, since some cables will melt easily from the heat of the iron. When using components, be aware of any bags marked with this symbol, as they are polarized and must be placed in the correct orientation, or you will get component failure. Remember when you're cutting the component legs that they can fly off in any direction if not properly secured.
Alright, this is the first video that we have. Where's my escape? Okay, so let's look at the second one. Since this one's not available, we'll go to this one.
All right, so I wanted to do a quick video on electrical safety. Safety is something that's extremely important, and obviously, we're speaking to people who are already in the trade or in trade school, and you need to get your safety training elsewhere for sure. We're not an official OSHA training facility or anything, but I wanted to just cover some basics, some undisputed facts about electrical safety that you should know. If you're a training manager or something at a company, you can share this with your staff to just help get their mind in the game with electrical safety. So I'm going to do another video, particularly showing how to use a meter in a safe manner, some of the features of meter, but this is just general conversation. We're talking about the anatomy of electrocution, so specifically how you get electrocuted, which is killed from electricity, arc flash, gear, PPE, lockout, tagout, fall risk, grounding and bonding, GFC and AFCI, and NFPA 70, the good old National Electrical Code. So we'll just go over this real quick. First is the anatomy of electrocution. So there's a lot of things that make a difference as far as if you're going to be killed, and a lot of it has to do with which direction it passes through your body. So if it goes, through your head and down through your foot here, that's very dangerous because it's traveling all the way down your spine and through your brain and also across your heart. So that's dangerous. Arm to arm is dangerous because from an arm to arm path travels across your heart or very nearby. Path is very important. But one thing that a lot of technicians say, it's kind of silly, is they'll say that it's not the voltage that kills you, it's the amperage. And while there is definitely truth to that, when we're talking about working on high voltage electrical systems that are connected all the way back to the main distribution panel, back to the transformer out at the street, you have nearly an unlimited source of amperage. If you get hit with a taser, it's true that you can get hit with very high voltages and not be injured, but that's because if you're hit with the taser is amperage limited. So it's a high voltage, but it limits the amperage. There's only so much amperage can travel through. But our bodies are a very resistive path. If you ever took a ohm meter and measured between your fingers and hand to hand, you would measure a very high ohm resistance, usually in the kilo ohm or mega ohm scale, which means that your body is generally going to, under normal voltage conditions, it's going to, conduct in these sort of milliamp ranges. And even at very low milliamps, you can, have enough of an electrical shock that it can electrocute you. Again, depending on the path that it takes. So there's a couple different factors to consider. One of them is the path. Just remember that the amperage that's going to be drawn through your body is really a function of the power supply and whether or not it's limited or unlimited, and the voltage. And so at all of these amperage conditions, in most cases, the power supply in the building is going to be enough to supply that much amperage. The question just is is how high is the voltage? This is, basic Ohm's law stuff. E equals I times R. So amperage is a function of the resistance more than anything else. So voltage and the resistance. And your resistance is going to be fairly fixed. Some people are going to have varying levels of resistance. Obviously, if you're standing in a pool of water, it's going to reduce your resistance. From there, it's really a matter of the voltage, which is why it's far more dangerous to work with 480 volts than it is 120. All right, so anatomy of electrocution has to do with the voltage. So how high is the voltage? Power source, is it current limited or is it essentially unlimited? And when we work in a building where you are connected to the utility, you have essentially unlimited current available. The body is not going to draw enough current to trip a breaker, so it's just going to keep sitting there shocking you until one of you give up. Then it's the resistance matters. So are you standing in a pool of water? Are your hands moist? Are you wearing proper gloves, protection that's going to help increase that resistance to a point that you're not going to have a current flow? On what direction does the path take through your body? Does it go through your central nervous system? Obviously, if you have a short, from one finger to another on the same hand, it's not going to be nearly as dangerous as if it goes through your body, which is why experienced technicians, when they approach a panel, they usually approach it with the back of the hand. And so that way, if it is grounded in some way, it's going to cause the hand to grip away from the panel versus towards the panel. The safest place to get hit with a current is in the back of the hand. And then duration, obviously, the longer that you're being shocked, the more likely you're going to be electrocuted. So to prevent electrocution, work only on safe voltages. 24 volts is generally considered to be safe if you're not without any significant PPE. When you get in higher voltages, though, you have to really think about increasing your resistance by making sure to wear proper gloves, rubber and leather gloves, make sure you're wearing proper work shoes, make sure that you have face shields, all that sort of stuff. We're going to talk about that later. And then think about the power source current. If you're connected to the utility, like we normally are on the stuff we work on in HVAC, that current is going to essentially be enough to fry you. It's going to just keep going until you're fried. The only exceptions to that would be things, like I said, like a taser, very high voltage and little pulses, maybe an electronic air cleaner, but it's not enough to severely injure you, at least not normally, because the current is limited because it's powered by a battery. So the amount of current is limited. Whereas when you're connected to a utility, it's just going to keep going. Now be very careful about the path that it can take. So make sure that your body is ungrounded, and obviously duration. You don't want to be alone where you could potentially be shocked for a long time. This is a handout from the American Electrician's Handbook from the 1920s. This is a real picture from a book that I actually own. And this just shows you how much has changed. These guys were brilliant when it came to the engineering of electrical, but this shows the type of bravado that gets people killed. It says electricians often test circuits for the presence of voltage by touching the conductors with the fingers. This method is safe where the voltage does not exceed 250. We're talking 250 volts they were testing with their fingers back in the 20s. And is often very convenient for locating a blown out fuse or for ascertaining whether or not a circuit is alive. Some men can endure the electric shock that results without discomfort, whereas others cannot. The next page goes on to talk about testing low voltages on your tongue, standing in water. It's crazy. This is before meters were common, but it just shows you how much has changed and how much more safe we've gotten in our mindset about working with electrical. Because this is nuts. Don't do this. The next thing is, we think about getting shocked or electrocuted as being the most dangerous thing, but arc flash is extremely dangerous. Anytime you get into larger commercial and industrial applications, it becomes very important that you are aware of the voltages that you're around, that you are aware of the devices, any open switch gear. Because again, while the goal is to always only work on unenergized equipment, when you deal with large panels like this, you may be working on an unenergized circuit, but you may have an energized circuit very near. Arc flashes occur whenever there's a bridge, some sort of electrical bridge where an arc can flash across. And the higher the voltage is, the higher the risk is of arc flash. It's something you definitely need to be aware of. When you think about arc flash boundary, you want to be really careful about getting no closer to the equipment than you need to unless you're wearing your full appropriate PPE. And I'm not going to go fully into what sort of PPE you need to wear, but just be aware that when you're working in industrial and commercial environments, including air conditioning systems, pulling panels off of higher voltage air conditioning systems, you need to make sure that as you approach, you are properly covered with your personal protective equipment, which is what PPE stands for. There's all sorts of different categories of PPE, all the way from the very basics. No matter what you're working on, you should be wearing safety glasses and gloves, protective clothing, long pants, proper work boots that are well insulated, leather type work boots, all the way up to category 4, where you're wearing the balaclava and the face shield and the high calorie absorption, arc rating of clothing. This would be the most extreme, highest voltage applications. But in a lot of cases, working on, high voltage switch gear in a commercial and industrial environment, you need to be in this category 2 or category 3 range. Again, I'm not going to cover all the specifics, but it's good for you to be aware that this exists. One of the most important things to have on your truck if you're doing electrical work is a lockout tagout kit. This is true of almost every segment of the industry. I don't care if you're residential, commercial, because for example, even in residential, you may do multifamily where you have to go between floors and you have to work on equipment that you're shutting off where you're not line of sight to the disconnect. And what a lockout tagout setup does is it allows you to independently lock a piece of equipment off at the disconnect so that you're the only one with the key who can unlock it to turn it on, and you can potentially put multiple locks in the lockout tagout lock, so that way if more than one person is potentially working on the equipment, you're all going to be protected. Everybody has to unlock it before the equipment can be turned on. It's very, very important, very practical. Certainly not, as some people think it's overkill, but it is definitely not. In a lot of cases, you're shutting off units at disconnects that are well away from where you're working, especially if you're working past the disconnect side. So say you're removing a rooftop unit or doing significant work, maybe to a disconnect on a rooftop unit, you have to definitely make sure that it's locked out and tagged out so that somebody's not gonna accidentally come along and turn it on. Another thing to consider with electrical, a lot of the deaths associated with electrical are simple shocks that then result in falling. And so you always need to be, properly tied off whenever you're working above 6 feet, according to OSHA. Again, I'm not going to get into all the specifics, but this is especially true when you're working on electrical, because the odds that you're going to fall are increased when you're working with electrical circuits, when you could potentially be shocked and fall backwards. Again, our goal is never to work on live circuits, but in many cases, some of those things may be out of our control. You may have some other live circuits that are adjacent to where you're working, and your shock risk increases. So when your shock risk increases, if you're working off of a ladder on a roof, then your fall risk also increases. You need to be aware of that. Because it's very important whenever you're wiring up anything to make sure that it's properly grounded, properly bonded throughout the structure, but also keep in mind that in some cases when you're dealing, especially with convenience outlets, anything where there's potential moisture involved, ground fault circuit interrupter, GFCI, is important because, like we mentioned, you could potentially be a ground path and not draw enough amperage to trip a breaker. And so a GFCI basically looks for imbalance between neutral and the hot. Again, this is for 120 volt circuits primarily. Convenience outlets is where you're going to see this more than anything else. But it's important to understand what they do and why they matter. And this is important when you're working with, extension cords and that sort of thing, which comes up a lot in the trade. GFCIs really will help protect you because, again, like I said, you can create a path to ground where it's enough to electrocute you, but it's not enough to trip a breaker. GFCI, by monitoring the difference between what's going in and going out, and if it sees an imbalance, then it knows that there's some leakage to ground and it can trip. Arc fault's a newer thing. I just don't want you to confuse it with GFCI. Arc fault actually uses a circuit board inside the breaker that looks at the potential or the possibility of arcs. And so if it sees a signal or a signature that looks like that there's an arc in the circuit, then that will trip the breaker. That's more for bedrooms, that sort of thing, to help prevent fires. So, GFCI is there to help protect you from being shocked or electrocuted. AFCI is there to help prevent things from burning down. So sort of different functions. And then finally, all electrical installations should be made according to the NEC, National Electrical Code, which is also known as NFPA 70. That's the National Fire Protection Association Standard 70. That's the Bible for proper electrical installations. And their goal, of course, is to prevent people from getting electrocuted, prevent fires, and then also prevent arc flash. But arc flash is more so covered by OSHA. So finally, let's just kind of sum it up. You got to be really careful about not working on energized circuits. You want to make sure to wear proper PPE. That's things like gloves, face shields, proper leather shoes, things like that to prevent you from getting shocked. Make sure that you understand that you could have a shock that would be well enough to kill you that's not necessarily going to trip a breaker, and use all the best practices to prevent yourself from being injured. So that's the basics here today. Like I said, I'm going to do some more hands-on demonstrations to show you how to use electrical meters to help keep you safe. Hopefully you found that helpful. Thanks for watching.
On the atomic structure of elements. So for example, let's say we have a copper element here, a copper atom, and we said that this is a good conductor. And we said the reason why. Why? Because there are 1, 2, or 3 electrons in the valence shell. What does that mean? That means that because we have so few electrons in the valence shell, they are less attracted to the nucleus. So again, in the nucleus we have the protons and the neutrons. Again, we know that the electron has a negative charge and the proton has a positive charge, and the neutrons don't have any charge, right? So we have that attraction, right, between the charges, where we have like charges are going to repel each other, right? And we have unlike charges that are going to attract each other. And so this attraction between the electrons all throughout the shells, this is the attraction that is keeping the electron coupled with the atom itself, right? So there's an attraction between the positive charges in the nucleus and the electrons, right? But again, as you can see with these rules of charge, unlike charges attract, and the distance between the two charges also affects the amount of force that is between them. So for example, if you have a magnet, right? You have two magnets, positive and negative pole, they're going to attract each other, correct? When you put the magnets closer together, the force is stronger. Do you guys agree? The same thing happens here with the electrons. So the closer the electrons are to the nucleus, the stronger the force that binds them to the nucleus, that attracts them. But we know that an electron can actually gain energy. And the valence electrons are the furthest away from the nucleus, so that means that the attraction is less, right? So let's make a note of that. Force So the attraction force is less on the valence electrons. These electrons can gain energy through heat, right? They can actually gain thermal energy, so the heat in the environment affects them. And another way that they can gain energy is if there's an electric field across the material that also causes them to gain energy. And we'll talk about that later. When they gain energy, what happens? Of course, they become free electrons and the atoms become ions. Okay, so this is the first step. So electricity is based on the movement of these free electrons. So again, if you will look at the structure of most metals or most conductors, right? You have a number of atoms that are organized in a lattice, what is called a lattice structure. So if you think the atoms are organized almost like in 3D, where there are metallic bonds between them. So I'm just going to draw this here so you can see this lattice structure. So this is how the atoms are organized. And notice, if this is the atom, we have the nucleus in the center, correct? And we're going to have the electrons around this nucleus. So we have electrons around. So there's lots of space, right? There's lots of space in that lattice for the electrons to move. And of course, while we have free electrons, the electrons don't stay free forever. What happens, they move, and as they move, they also lose energy, right? So electrons lose energy. As they move. And what happens when they lose energy? They come down into a lower energy level, and say for example, an electron gains energy, it leaves here, it moves here. as it moves, it loses energy, and eventually is going to go and join another atom, right? So when it leaves here, this becomes a positive ion. And of course, that positive ion, it has a net. The net charge is not neutral anymore. The net charge is positive because it just lost an electron, correct? So now we have more protons than electrons. And so that ion is a positive ion. It has a positive charge. And we said, based on the loss of charge, that the electron is going to be attracted to that ion. Of course, it's going to be attracted even more because the ion is not neutral. It has a net positive charge. And so an electron that has lost energy is going to join a positive ion, and it's going to become neutral again, right? And that process happens simultaneously all over the material, all over the wire, right? So that is why when we close a circuit, we have, for example, when you turn the lights on, you have the light turned on at the same time, because all throughout the material you have free electrons moving, and this is how we can show that electrons move throughout the conductor to complete the circuit. Now, what is the circuit? The circuit is a closed path for electrons to flow, right? A closed path for electrons to flow. So again, here is an example. Again, a circuit is a closed path for electrons to flow. So here's an example of a battery, right? So we have a simple battery here. Now in the battery we have a chemical reaction. Is that right? Let's say this is a light bulb. In the battery we have a chemical reaction that generates free electrons. Yeah? So we have a reaction happening, we call it a redox reaction. And it generates free electrons. These electrons leave the negative terminal of the battery, and they are moving to the positive terminal of the battery, right? That is how the reaction continues, right? You need to have the electrons going from one side to the next. The electrons, when they are produced, they have a high energy level, and as they go through the lamp, they actually perform work, right? That energy is converted into light energy. So we have light coming out here. Okay, they perform work, the energy is